studied mechanical engineering.
Awesome. How about you, Dave?
I'm David Aviation. I came to the United States in 2001, and I went to Cleveland State University and studied electrical engineering.
Awesome. Okay, great. Okay, so the topic for tonight. So if you think about our world right now, we've got lots of electrified automobiles, some of them fully electric, some of them hybrid. I think, Claudia, I think you came in here on a rental car that was a hybrid vehicle. So these are standard and all over the place. So we're here to talk about electrified aircraft. So is there what do we think we're going to gain by having electrified aircraft, and where do we stand in that? What do you think are the main benefits that we're looking for?
It's a really good thing to think about because, as you said, we are starting to see all these electrified vehicles on the road. So it's only natural that we would think what's next and what can we gain from the vehicles and apply to aircraft. And there's a lot of questions that can be answered, and one of the things that we're looking at within NASA is what does it do to emissions? So the goal is zero carbon emissions, lower acoustic emissions, so lower community noise. We all have experienced those very loud airplanes as they come into land. So there's some acoustic benefits. There's some reduction in costs because of the increased efficiency. And also, as I'll explain a little bit in my presentation, is we can take advantage of electric propulsion in a way that also enables lighter and more efficient structures as well.
Awesome, great. Okay, whole set of benefits there. So, Dave, any others you'd like to add or talk more about?
Sure, I think one of the main benefits of electrified aircraft propulsion really will be the benefits for the flying public and how it will decrease the cost of air traffic.
Okay. All right, great. So maybe, Claudia, maybe you can dive into that a little bit more. So you're working on a set of technologies, not only developing these technologies, but also looking to demonstrate them on an aircraft, the X-57 Maxwell. Perhaps you can tell us a little bit about that. You know, tell us about that project. What are we really looking to learn from it as well?
Yes, absolutely. Definitely always enjoy getting to talk about what we're working on at NASA. And as you introduced the project that I'm going to speak on, is the NASA X-57, and it's NASA's first all-electric airplane. And you see two names there. So Scepter is where the project started, and it's its first project name, and it's transitioned to more of the X-57 Maxwell as we became an experimental airplane. And also we wanted to link ourselves more to the electric world a little bit by taking on the name of Maxwell, who's the physicist that's attributed with a lot of work in terms of the physics of electrics and a lot of the laws that we use to design electric systems. And you start to see just by looking at our project logo what we're trying to accomplish. There's pieces of it that look like a normal airplane, and then when you look at the wing, you start to see the differences. And I'll talk to what all the smaller propulsors do, which we call the high-lift propulsion system, as well as the motors on the wingtips, which we call our cruise motors. And we're going to do this by starting with the baseline airplane, which is a Tecnam P 2016, and we wanted to take this airplane so that we could do a comparison and be able to show that we are actually seeing the benefits that we expect to see from electrifying an airplane. And what we did for what we call the Mod 1 is really just add a lot of data, or the ability to take data from this particular platform. And as we're walking through this animation, I'll pause for a second here. For Mod 2, that we then replace the conventional gas engines with the electric motors, and it doesn't look very different on the outside, but when you look at the components that are being introduced to the inside of the airplane is where you start to see the difference. So here inside of the fuselage, which I'll go through each of these components later in detail, but we added 800 pounds of batteries, and as well all the cabling and all the wires that have to then run through the fuselage and then through the wing to get to the newly electric motors that are added for Mod 2. But again, the point is that we can still be able to fly at the same points in the sky as the baseline vehicle, so we can do those comparisons and start to quantify what are those benefits gained. As we move into the modification 3 for the airplane, you can see there's a couple things that start to change. First, we removed the baseline wing and added a skinny or a high aspect ratio wing, and what this does is then it alters the flow that's occurring around the wing, so it becomes more efficient at cruise speeds. So it starts to actually affect the way the airplane flies through the sky, and it already increases some of that aerodynamic efficiency. And the other thing you'll notice is we moved the electric motors out to the wingtips, which then introduces a whole nother set of questions in terms of flight dynamics. There's a whole nother layer of questions of what happens if you lose one. How do you protect the pilot from the large yaw moment that occurs at that instantaneous loss of propulsion? And I'll talk through all of these different aspects as I walk through my slides. And finally, the modification 4 version of the airplane comes into play when we add the high-lift propulsors on the inboard of the wingtip motors, and this is the culmination of everything. So by adding the high aspect ratio wing, we increase the efficiency at the higher cruise speeds, but now we introduce this high lift propulsion system so that we can regain that performance at the low speeds and be able to do a full comparison across the flight envelope. And here is where we start to see the benefits of not just electric propulsion, but the fact that now we can introduce this concept of distributed electric propulsion. And there's a lot of benefits that can come with that in terms of the efficiency and what kind of structures we can use, but also how we can add some redundancies even to the system, which increase the safety of what we're trying to fly, which is always a big question in terms of flying electric airplanes. And this will be the final phase where we'll be able to collect data for the full flight envelope and do a direct comparison to the baseline Techno vehicle and show that we do have the benefits that we were looking to gain. I'll talk a little bit more about distributed electric propulsion, and you saw how those propellers, they extend and they retract at certain flight conditions, and that it's not necessarily a new kind of technology. It's a technology that you see a lot on gliders, but what we've done is we've coupled that with an efficient structure along with electric propulsion. Again, those benefits that we can introduce into the airframe design by having this concept of electric airplane. It really opens up the design space to an area that before maybe we hadn't looked at. And the wingtip motors are another great example of this. This is not anything new that we've looked at, but with electric propulsion we can add that back in and also bring with it the safety features necessary to counteract some of the concerns that come up with having propulsors on the wingtips. And so you can see here on the plot that's shown on the screen just how the efficiency is able to increase with the different architectures, and you can see where X-57 as a DEP type of system lands and how it compares to even the conventional general aviation aircraft, and that's already a significant improvement. I always like to show this particular graphic because it overlays the X-57, the final Mod 4 configuration with all the high-lift propulsors and the wingtip propulsors also included, but it shows how much smaller the modified wing is compared to the baseline wing. However, we can still achieve the same or even better type of aerodynamic performance. And DEP, as we're introducing it on X-57, is really just a start, and Dave will talk more about this later, but really the goal is to eventually spread this to other modes of aviation and other sizes of transportation, because we've seen that we can really see some great improvements in efficiency, which is what we're after. Of course, with any new system, as we take it to flight, we start to run into challenges, and one of the big challenges that comes with electric airplanes is what do we need to test to show that these systems are safe and that they have the reliability that we need them to put them right next to a person in the sky. It's not just like in a car where you can pull to the side and run away from a car that's on fire. You have to deal with it in flight, which we want to avoid having to deal with it. So this is a stand that we built out at NASA Armstrong, where we've tested. The hardware that you see here is actually the cruise motor that's going to go on the modification too. It's actually part of the integration process as we speak at NASA Armstrong. I talked a little bit before about the 800-pound batteries that get introduced into the system, and this is a big overview of the circuit that we essentially want to put in the sky for flight. And you can see the batteries and how they connect to the cruise motors, and one particular characteristic to highlight is the redundancy that exists, even just, again, when looking at what are those safety mechanisms that we want to employ in the design. Batteries are a big developmental aspect of electric airplanes, and we have to show that they are safe and ready for flight as well. This was one of the tests that we did to examine the battery's capability to contain a thermal runaway, and as you just saw, that did not contain the thermal runaway. This was not something that was supposed to happen, but I always refer back to Neil Armstrong's quote that we fail on the ground so that we don't fail in the sky. And this was a great find. It was something good, even though it was we needed to go back to our design and do some sort of a revision. And so we did. And in fact, the updated design worked so well. And you can see the battery here in the middle. And you actually can't see what's happening in the battery. So we had to add these IR cameras that show you what these images look like. And you can actually see here as the thermal runaway starts to propagate, the actual design that we've implemented is able to contain it. So that was a very successful piece of X-57, and we're looking to build up this knowledge base with all of these different components that we're developing. One of the nice things about NASA is we're able to share all this information, and eventually that's our goal, not just to share it with the small companies so that they can also learn from what we've learned, but also with the FAA so they can also start to understand what requirements they need to levy on all these companies that are emerging with these electric vehicles, and especially when we think of the concepts like UAM and those kinds of new architectures being developed. The flight envelope, as you see here, shows what we're doing. This is the full range of the baseline airplane, and as I've mentioned multiple times now, with the wingtip motors, we gain what we call the normal operating range, so we can compare that range of speeds, and with the high lift system, the inboard smaller propulsors, we regain the slower speeds, and then we can do a full comparison. In its full culmination, this is what a Mod 4 configuration flight will look like. The airplane will take off with the high-lift propulsion system active, because that's the slow-speed regime, so that's where it'll need it for that extra lift. Once the airplane reaches to cruise speeds, those high-lift propulsors will fold back the blades, and the cruise motor system on the wingtips will take over as the main source of propulsion. And that is what we are aiming to fly to.
That is awesome. I think I may have added something to my bucket list, and that is to have my own aircraft and have it be electric powered. So I'm really excited about this, especially I love the way that you've described the way in which this technology is being developed. Crawl, walk, run, and then fly. It's very exciting. So if I'm going to have this on my bucket list, I'm going to have my own electric aircraft. I realize that the X-57 Maxwell is one of the necessary steps to making that happen. Can you talk to us a little bit about the timeline for the flight of that vehicle?
Absolutely. I did allude to it a little bit right now. We have the cruise motors that are going to go, or the version of the cruise motors, I should say, that are going to go in the inboard locations as part of Mod 2.
Okay.
And that is scheduled to start flying at the end of next summer.
Awesome. Okay, great. Okay, so when we look at that, that's X-57 Maxwell is a general aviation size aircraft, so a smaller aircraft. And so it makes me wonder about larger electric propulsion systems and larger aircraft, the type that we fly commercially. So where do we currently stand in terms of that, in terms of larger vehicles, and where are we headed? And Dave, I wonder if you can talk to us a little bit about that.
Sure. NASA is investing in electrified aircraft propulsion research, and it's doing it as part of a portfolio to improve fuel efficiency, emissions, and noise levels in commercial transport aircraft. NASA is working across a range of markets, from urban air mobility, presentation of which you could have seen 2 weeks ago in this webinar, and also to subsonic transport, and working with industry partners to develop technologies and then eventually transfer those technologies into commercial sector that then they can develop future products and markets. However, the question which you actually asked